Can I ask?
Yeah, if you can. Sorry.
Never just how much is it?
Fine, now we are set.
Speaker?
No, we are set. We are set now.
Okay.
Hello, sir.
All right, good afternoon.
Good afternoon.
It's not afternoon.
Good morning, brother.
It's still morning. Okay, we are told, okay, the first one is A, the second one is B. Okay, we in our heads it's like morning, afternoon. No. All right. You're most welcome. Good morning, class. And we're just going to continue with what we have been discussing, but we're just going to have a recap, just a little recap of what we did before, for the sake of those that are just joining us, and then for better understanding and flow. Just like I told you the last time, I'm sure most of you know already, and some of us have made some efforts to be part of the center. I am from the Collaborative Center on Artificial Intelligence, which is here in Cosmopolitan University, and you wonder how come we have a dedicated center. In fact, that's actually the nucleus of the school. So we are trying to introduce digital technologies in our learning. We are trying to introduce digital technologies into our learning. And I hope you know that artificial intelligence is just one of them. There are several digital technologies. And so the center tries its best to make sure that both staff and students and partners externally are at home with these digital technologies for our learning, for our teaching, and for our professional development.
We have some complaint with the first class. If you know away from the system, they can't hear you.
Oh, really?
That's why I said,
Okay. Thank you so much. So I'll stay. So I'm going to be fixed to this place. And naturally, I like to move around when I talk. So, but today, I'm going to be fixed to this place. Not too far, right? Okay. All right. Okay. So I don't know if they can hear me online, virtually. Okay. So we'll just continue, just like I was saying, try and be part of us. If you have other questions, we are there. We have staff that will help you address issues as it relates to artificial intelligence and digital technologies and so forth and so forth. We give trainings, we give um, teachings, we do research, and so many other things. So let's proceed. Last week, we tried to understand the differences between machine learning and conventional programming, and we introduced our neural networks yesterday. How many of us remember what we did? This class is so full today. A lot of people have been to travel. So don't worry. We'll try to make it, I'll try to wrap up in time so that we can do it. Students are going back, so they are excited to leave. So let's, just like I promised, let's have a background. In the last module, we talked about AI. We tried to understand what artificial intelligence is all about. It's just machines trying to be intelligent in the sense that they are trying to do what humans can do using their own knowledge. This one is not humans this time around, is the machine doing and acting as if they have an understanding of life concepts, life problems, and life solutions, and they provide solutions. That is, if we want to say in a nutshell, what AI is all about. And that brings us to the different concepts as it relates to artificial intelligence. And then we looked at the different branches of artificial intelligence, just like I started. And I told you digital technologies. AI is one of them. If we go down memory lane, AI is not that new. It's just that because of the tools that we have now, especially ChatGPT, it now looks as if, oh, AI is just coming out. No, AI has been there for years and years. But it has been progressing until where we can see it today, where we can talk about generative AI. And just like I said, it is a tool. AI is a tool. It's supposed to help you, assist you in your endeavors. That is why it is a tool. And that's why we are trying our best to know how to use it properly and know about it. Most of you that are here, you're not just satisfied with using it, you want to know what it is, what it really is, how it really works. And I will say you are good, you are in the right place. And then we talked about machine learning, deep learning, which is actually neural networks. What else did we talk about? Robotics, which is a branch. Natural language processing, NLP, you've been hearing natural language processing, and then we have our fuzzy logic. Yes. These are terms, but when we say machine learning, this one is not the humans that are just learning now. There are different instructions and rules that is now imputed into a machine, and then you add input or data, and the machine is learning and acting as if it is human. Machine learning in a nutshell. And then we progress from there, and this course is about deep learning. That's a notch higher. We're going deeper into machine learning. It's actually machine learning, but the more of it, if I can be permitted to use that. And then we are borrowing a leaf from our neural network. We just say neural network. We are talking about, we are borrowing a leaf from the biological neuron. You know what the neuron is in the brain. We'll talk about brain. When you talk of neurons, we're talking about our brain, how the brain works. And so machine learning is talking about how deep you can process different activities to bring an output that makes sense by way of background study. There's so much we discussed, and we tried to see the structure of a neuron biologically and the artificial neuron. So the neural networks we are talking about in deep learning is actually the artificial one, not as complex as the natural one, but equally, interesting. That's actually I would say, a kind of basic ingredient when we talk about our deep learning. So I'm highlighting that point there because today we have discussed the first one. Today we are going to demonstrate an understanding of the advanced neural networks and understand the application. But before we do that, let us know some concepts. We said it in passing in the last class, and I just said it now, but let us be more specific. Intelligence algorithms. When we say intelligence systems, machine learning, when we are talking of those things, what is intelligence? Ability to understand, apply, and do without intervention, so to say, just like we have our normal intelligence in our daily lives. But now this is machine intelligence, and so when we talk of intelligence algorithms, is there any one of us that does not understand what an algorithm is? We know it's a set of rules and processes that you operate to solve a particular problem. Not share background again. And so this time around, we are looking at algorithm biases. We want to look at the bias. Why are we looking at this? Eventually, we are trying to understand and build or work with what we call our deep learning architectures, the kind of architectures we use for our deep learning structures. Do we get it? And so we are going step by step, like what we try to do in this class is to give you a solid foundation so that by the time we get there, in fact, from the morning class, by the time we get to the fourth slide, we already are balanced with what we mean when we talk about deep learning in this slide. And so we'll look at the first two major biases that we face: data biases and design biases. I'll explain it, so just stay with me. Can you just give me a minute? I need to just write something. I'm sorry about that. We are trying to handle the all right. Biases. When we say a bias, in your first class, do you understand what a bias is? That's what do you understand by a bias? Please, let's just explain. Yes. Why did you say me? Explain what a bias is, as it pertains to machine learning and deep learning. What is a bias?
to go to the much I know about it. I think it's almost similar to the bias relations, like English, having all of this like
Ma, can you hear him? No. And the people online needs to hear what you're saying. So what's the bias?
I think it's more like catalyst, right? It's a nudge towards a particular direction. That's the understanding of bias. So in deep learning, the more to understand it, it's used to adjust.
No. Yes, please. You are going deeper. Just tell me bias instead of deep, like machine learning. Come on.
Bias as a data bias.
Yes.
For example, when you're on, like most of us spend a lot of time on social media. So wherever you are on social media, let's say you're on a political forum, wherever your interests are, the data algorithm will master your bias and it will push you towards content that exists in that space.
That's more of recommender. It's a kind of it's called recommender systems. It's kind of looking at the kind of recommendations it will make to you based on your interests or where you have been. That's more of recommendation. But when we say a bias, when we say the data is biased, let me give an example. And I'll use the one that is very common. You should, just like I encouraged the class in the morning earlier, I said, read about most of these things. Just go online, read about them. Look at news. There are different newsletters that are talking about AI and all that. There was one that I found very, very, what will I say now? Very intriguing and concerning. Yes, that's the word I'm looking for. I found it a little bit concerning. We'll talk about that later. But let me just give an example of what a bias can be. And then there's this Google platform that we use for teachers, and then you were to feed the AI. AI feeds on data. You were to feed the AI with the drawings of a ball. And so everybody was like, they'll draw it, but the way they see the ball, and later they ask the AI to show a diagram of a ball. And so the AI just goes like round thing with some designs inside, no matter how round. Is every round thing a ball? Is every round thing a ball? The AI is biased because why? Anything round, just round with some designs. Okay, let me use another one. They asked the AI to collect data of shoes. Do you get it? And so people were drawing, they said you can just draw. And so they draw shoe. But this AI was designed in the West. It was European, outside the country, not in Nigeria. And so most of the shoes they were drawing were canvases, things they call shoes that we don't call shoes. And so as this kind of shoe, you want the AI to bring it. And it brings that shoe that the AI was trained with, the diagram of the shoe that the AI was trained with. That's bias. The AI is kind of biased based on the data it has. And it will give you something that it feels it is, because that's what you trained it and told it that is what it is. It's like training your child when you see an old person slap him. And then the child slaps the old man and you're like, why are you doing that? I was trained to do that. Do you get it? So that is what we know as bias. That is what you call a bias when you're talking about that. And now the big one that I said got me a little bit concerned. There has been different input data about criminals in some parts of the US. And most from the record that the AI had, most of the data that was given to this AI about the criminals in this part of the US were blacks. And so at another point, it was asked, who is more likely to have committed this particular crime in another crime scenario? The AI just pointed the black man straight on. That is bias. It could have been, yes, it's the black man that did it, but it then could have been the white man. Yes. Are we going to be offended by the AI? No. Are we going to feel racism? This is not racism. This is AI, and this is bias. So we try as much as possible to mitigate bias. How do we mitigate bias? We try as much as possible to give data that will not cause that kind of bias. And so you can just imagine the amount of data that you need to feed the AI with, so that the AI can separate which is which. Do we now understand bias? Taking us to our data biases, perception of systemic or historic biases. The historic there, just think about the history it has about the black man. Most of them committing crimes in that particular locality. And so it gives you that. That's a bias that you should mitigate when you are working in a deep learning environment. Do we understand? Do we understand? And so, next, do we have questions before I talk about the other bias? Next, we're talking about our design biases, innate prejudices in the coding of the algorithm. This basically talks about style. And will I say style and culture? Culture can come into play here. What am I used to? What do I see as the norm? What do I see as proper? And what do I see as trash? Something not to be considered. If this is how I have been doing it, why do you now want to come and tell me that I should do it differently? That's design bias. I'm designing it in this particular way. That is where we are trying to come in, so that there will be a structure, a proper structure that will follow when we are creating these algorithms. So that when we have a structure, there's all these biases will not come into play, right? But right now, we have this kind of biases in our so-called intelligent algorithms. They are there, but you have to look out for them, and you have to work with them. You have to mitigate these biases so that your output can be as accurate as possible. Do we understand? All right, so let's proceed. Next, weights and biases. We are talking about parameters. I want you to learn these terms, because as we progress in this course, we are going to be using these terms, and I will not be explaining to you what the terms are. You will already know. And don't worry, you know the way we try to do it here, we try to make it as clear as possible, so that you can use it easily and understand exactly what you're doing. Weights and biases, they are what we call our parameters. They are adjustable values to try to reduce the value of our loss function. Hang on with me when we are training our machine. What are those adjustable? You can adjust your weights. And what are the weights? They are the inputs that you put. Any instance of anything, they can be your weights. These are what we call the weights. And then when we go in depth into weights, you can now see the structure of the weight. And then just like we talked, the biases, the different biases that that come into play. Whether is it a data bias or is it a design bias, we mitigate all these and we call them your parameters. What are you aiming at? A loss function of what?
Zero.
Yes, or as close as zero as possible. That's what we're talking about. Now, what is a loss function? We mentioned it last week, but let us go into loss function now. This is something, like I told the first class, some of us can use our generative AI tool and we just appreciate what it does for us and try to change the prompt and are satisfied or we are not satisfied. For those of you that are going in depth into this learning of artificial intelligence, do you know what you're looking at? The value of your loss function. You're looking at the value of your loss function. Is it good enough? Especially when your activities become more and more complex and you want to get more from the system. A mathematical process that quantifies the error margin between a model prediction and the actual target value. Model's prediction and the actual target value. Does anybody have any gray area concerning that? Do we understand that? When you are using an AI, you want it to do something for you, right?
Yes.
When it does it for you, that it gives you an output, there's something you expect. What if it is way out of what you are expecting? There's a problem, right?
Yes.
And so you try to find out why is it not giving me what I really want? There's a difference between its prediction
And the actual target.
and the target value. That is what we call the loss function.
Okay.
So when we say the loss function is 0, wow. It's just like in the first class, the person said the system is what? Perfect. But when the loss function is far from 0, that, look at it, the error margin. When it's 0, no error. But when the error margin is high, or further away from 0, you know that there's a problem. And so you have to work on your loss function. That is what we mean by loss function. So subsequently, when you hear loss function, you know what I'm saying. Now what I'm expecting is not what I'm getting, or what I'm getting is exactly what I'm expecting. Loss function. Are we okay? So let's proceed. Role of the loss function. That is why I say when it's just somebody that wants to just use it, right? Who cares what the loss function is? Some of you will even say, close enough, it's okay. Let me just use this one and add 1 and 2. You get what we want. But for you that are experts in it, you're actually looking at your loss function. And these are the rules of the loss function. I've explained most of them actually. Performance measurement, a clear metrics to evaluate the model's performance. You might find yourself in a situation, maybe in the office or in your private practice, where you will need to give a report on the performance of this particular AI. The loss function will tell you what is going on and to help you. Direction for improvement. And it directs and adjusts parameters which are the weights. The parameter is a combination of what?
Weight and bias.
You shouldn't answer.
Oh.
It's the weight and the bias. So what it does, the direction for improvement, you kind of like tweak your inputs and adjust it. The only thing that can help you do that is your loss function. If you do not know the loss function, what is that error what? If you don't know the error margin, you will not be able to determine how to give direction for improvement of the system. And then balancing bias and variance. And then I talked a little bit about oversimplification and overfitting. In your last class, do we understand oversimplification and overfitting? Okay, let me start from overfitting. You want your system to do something, right? What do you do? What do you give the system? what do you give to the system? What do you give the system? Good. You feed the system with data because you want it to perform a particular task. And then that's how you feed the system. You feed the system. You feed the system. You feed the system. They told you that AI feeds on data, and so you overload it with data. You know, it can happen. And then by the time you ask for a result, it gives you a kind of complicated result that you don't even understand yourself. That's overfitting. You have just experienced what you call an overfitting. But with an understanding of the loss function, you'll be able to mitigate that. You'll get it. And then the opposite of that is oversimplification. Do we understand? Okay. And then finally, it will influence the model's behavior. That's why we have the certain loss function can affect the model's behavior, such as being more robust against data outliers. Those extra is giving you as by way of the results, and the outputs is what we refer to as outliers. Are we okay? This, I particularly found it interesting from this site, datacamp.com. Please go there, visit it. It's so beautiful because I like the way they illustrate most of these AI concepts, especially the concepts. They explain it, they illustrate it, and it's so beautiful. And this is just one of many. There are so many other sites. Sir? Come. Yes, there are so many other sites that you can use to, learn more about this concept. Please do well to learn about them. I just had to get them out because I particularly like them, and so many of their affiliates, which is very good. Now, we have learned about the loss function. There's another function that is very necessary when we are talking about deep learning. And that is our activation functions. The activation functions. What is your activation function? Let us go through it. Let's take the first point there. It says the integral building block that enables neural networks to learn complex patterns in your data. To learn complex patterns. We talked about simple patterns. And then complex patterns. How do you learn about these complex patterns? It's the use of the activation function. How many of us remember that diagram? What did you call it the other time? Like a beehive, like a mesh diagram. You are looking at different nodes, inputs, and then you have hidden layers, and all those hidden layers, they are bringing one output, just like the biological neuron. You have the nucleus, right? Working with all these different nodes to bring us a simple output. Just one. But what is collating everything together? What is analyzing those activities to make sure you bring out something coherent that you want? It's our activation function. That is what works. Don't worry, I'll show you another structure that will throw more light into that. They transform the input signals. Remember, we have input signals, which is the data you feed into it, right? The input signals of a node in a neural network into an output signal that is then passed onto the next layer. There can be single layers, and there can be multiple layers that are hidden, we will call the hidden layers. Okay. Thereby ensuring that neural networks are not restricted to modeling only linear relationships between inputs and outputs. If the activation function is not in that deep learning process, do you know what happens? It's as if you are doing normal conventional programming and your algorithms are basic. Garbage in, garbage out. Just like that. Simple. Fine, you can tweak it a bit to give you some kind of results, but most of your results will just be new. But by the time you have additional complex interpretations of your data set, the person that is doing that is your activation function. It's actually a very powerful algorithm that is in the system. So you cannot do without your activation function. And then finally, we said it allows neural networks to learn highly complex mappings between inputs and eventually your outputs. Let me use the example I used in the first class. Like last week, some of you became medical personnel, where we talked about different parts of a neuron and how it works to bring an output, which could be a response to a stimuli. This time around, we use pain. If I carry a hammer and I put your hand and I hit it, even before the output, some of us here that are watching it will do like this, out, because you are expecting what's the expected output? Pain is the expected output. The input is what? The hammer, the impact of the hammer, the input. What is it that processes, there was an action that took place, an input. Something happened inside you, it goes straight to your brain, and your brain works on it and brings out an output of what? Pain, that you felt, the activation function. That is activation function. Does that explain?
It dissects any kind of information that enters and gives you a result.
That's what it does. Basically, that's another way of putting it. But I just want you to get that concept. Do we all get that? That's our activation function. Look out for your activation function when you are designing, when you are using an AI system. Look out for it. That's to tell you that sometimes there might not be an activation function or a dead one. And what do? Look out for it and make sure it is there and make sure it's good enough and it's doing what it's supposed to be doing. Yes.
Can I say that it's naturally in there? Because you can't have like a system and you give it input and it just give you output. Like it has to process something, and something has to be there. So naturally, the system already has that activation function. It's just that it's, how should I put it? You enforce more emphasis on the activation function itself. Using that.
Naturally, a deep learning system should have an activation. Just like naturally, normal human beings have a brain. So why are we referring to it? You can have a basic machine learning architecture without the expression. Then it just goes input, and then you get your output. But remember, let us remember, this particular module is talking about what? Deep learning. It's introduction to deep learning. So naturally, you have the activation function. So as we proceed, we begin to see the architecture of the deep learning architecture, and we begin to see the complexities behind the activation functions. All right. So now, from all that I've said, we have this. We have our input. This mathematical structure is trying to tell us the basic structure of our deep learning. Look at it. You have different inputs. Are there 3 there?
Yes.
Yes. No. Yeah, infinity. Any number.
How many of you say they are only three? Look at it closely. I want you to really look at this diagram. Look at your inputs. Are there three? Look at it again.
Yes, there are three.
There are three.
Yes.
Three. The inputs. Look closely. Look deeply.
The dot signifies to any amount of input you decide to do.
Look deeply. How many of you said there are more than three? Why did you say that?
Because of that expression of
And she saw the dots. You would not look deeply. This is deep learning. Sorry, just asking. The inputs here. See that N there? 1, 2. You see the dots? That dot N. N can be any value. It can be 2 million. From 1 to. Do you get it? So that's what the structure is trying to tell you. You can have a whole load of inputs coming into the system, and then it produces. These are weights. These are different weights. You can see the N there. The N is an unknown. Can be any value. And then these weights, they combine with the biases. And the summation of the biases and the weights is what? No. What did you just see that they are called? The summation of the biases and the weights that we get. Good. Louder. Parameters. That's our parameters. Remember what we said earlier. So those are our parameters. And all these parameters, when we feed it into the system, it has to go through what? The activation function before it can give you an output. The activation functions works on your parameters to give you the output. Are we there?
Yes.
Okay. So we understand the process. This is just like a summary of what we have been trying to say. So you can see next time when we are talking, we'll just say the activation function, the loss function, and so forth, and we are together. Yes, please.
Well, I'm just curious. All this was how to the back end, like does it use green code
Yeah. When we say algorithms, what drives the algorithm? When you have the algorithm in place,
So there must be a back end code
you must be, you code it later. That's why you're here, right? Not just to use ChatGPT. You have to know the building blocks, and you have to have an understanding of how this works. As we progress, you'll see what we're trying to say. Yes. You see the process? The deep learning processes. First of all, we start with the data preparation. Please, let us go step by step. I want you to get the concept, okay? So for data preparation, we have there, the first point says, the network is fed with large data sets, like we have already explained, of labeled examples. Each example consists of input data. We have talked about our input data, right? And then they are given examples there. It can be images, it can be text, and corresponding output labels, classes, predictions. We are using predictions because we are talking about the machine here. All right. So the next step in the deep learning process is what? Forward propagation. And what is that? The input data flows through the network, just like you saw in the diagram before now. It flows through the network layer by layer. You remember our mesh diagram where we have different layers. It goes layer by layer, and those layers, the activation function works on them, with each layer applying a set of learnable weights and biases to the input data. The output of each layer passes through an activation function, which introduces non-linearity in the model. There's nothing I'm saying here that we've not talked about this morning, right? Good. So next, the error calculation. When we talk of error calculation, what are we talking about? What are we talking about when we are talking of error calculations? Don't read. You talk like an AI person. Error calculations. So don't read it. Thank you. All right, the error calculation, we are looking for the loss function, and that's what it says there. It says the network's prediction are compared with the true labels, and the error signal is calculated using a loss function. The error signal measures the difference between the prediction and the expected or the desired output. And next, this one we have not talked about, but this one usually happens in the deep learning process. Unconsciously, you do it with ChatGPT. How many of you have ever gone back to your prompt and tweaked it? How many of us have done it? Have you gone back to your prompt? You've done it, right? You've gone back to your prompt and adjusted it, and then you feed it onto the AI and it gives you another result, right? Something similar. We'll talk about back propagation. The error signal is propagated backwards through the network. It goes back through that same network, okay? Layer by layer to calculate the gradients of the loss function with respect to each of the model's parameters. And then the gradient represents the direction and magnitude of the changes needed to reduce the error. There's no big deal there. It's just like soup. I mean, you make a pot of soup. Guys, you cook. There's somebody that cooks. But I know the soup salt. If the salt is too much, what do? You add some other things, you go back and then go back to the pot and try to adjust it and all that. That's just what we're saying. That's so big. Go back. Your gradient will determine complexity. That's determining the amount of salt that you and the amount of extra ingredients that you add to that soup. Or if the salt is not enough, the amount of salt. By the time you go back, that's what we call our backward propagation. And then we have the last one. The iteration seems to be the last one, but the iteration is just going back again and again. And I'll tell you why. The weight updates, the model's parameters, that's the weights and the biases, are updated based on the gradients and the learning rate of the machine. Remember, anytime we're talking about this, we're talking about the machine learning from all this. And the learning rate controls how quickly the model adapts to the new information. And then the iteration, you go through the process again and again and again and again and again. Why did I say I'll come back to this? Because if you look at this one, you've already you have the data in the system, in the different system already. And then you see that your activation function is doing all this again. That is your iteration. The activation function, it doesn't you don't need to know this one. You're not reading the data. You're already included it, right? And so you see the activation function working, going back and forward propagation is okay, backward adjusting and bringing your final output based on that. What have we just described? We have just described our deep learning process. This is our process of deep learning. All the time. The way your brain works is constant. It will change. Say something will change. What will go wrong? But You know, it's just that simple. Understand that. So let's go. Let's proceed. Do I have any questions? Please, do I have questions online? No questions online. Can they hear me? Yes. Yeah, okay. Thank you. All right. So, how are these processes achieved? How is it achievable? Because we use different mechanisms. What some of you can call techniques. What are those techniques? I put 4 here. Feature extraction, hierarchical representation, distributed representation, and finally, abstraction, which I see as one of the most important ones. Because if you look at the feature extraction, they extract relevant features from the input and they use it to make prediction. What does that tell us about feature extraction? What does it tell you? Please just look at it closely. Look at that definition closely. What's it telling us about? Okay, you put a whole load of data. You impute a whole load of data. But it's telling us that extract relevant features from the input data, which is then used to make predictions. The system is so good that it does what? It doesn't use all the data that you give to it. It uses the relevant ones. That is feature extraction. That's the technique it uses. It's that powerful. And then next, hierarchical representation. There are key points there. Represent data in a hierarchical manner with early layers learning low-level features and later layers learning high-level features. It's layer, you saw those hidden layers we talked about last week. From layer, but it follows a hierarchical pattern. So one is learning from the other, getting better. Okay, let me just give this. Have you noticed, because there was a lady here in the morning, and she was like, anytime I go back to the AI and feed it with new data, it gives me a more informed output. Why? Every data you feed it with, what does it do? It saves it and learns from it again. And it keeps learning, and it keeps learning. You know, so there's a hierarchy of understanding. The machine is understanding more and more based on the updated data. Remember from the last slide, we talked about the weights updates. Based on the updates that you are giving it, it's learning and learning and learning, and it's getting better. And that is that feature, that's a mechanism that is using in that process. And then the next one, we are looking at, hey, another class there. You guys, what is going on there? Just invited me. Right? Let's share. If there's any discussion, let's talk, let's be together. We are almost done, actually. So I don't have to put anybody to sleep. We're almost done. I told you, we'll make it quick because people are going for holidays. All right? But how come you're not asking me questions? Ma, it's just quiet. Are you understanding everything? It's either you're understanding everything or you're not understanding anything. So which one is it? You're following, you're understanding. No, I'm talking to your friend at the back there. Are you okay? All right. Do I have questions online?
No, ma'am. Yeah, good.
This is serious. Okay, I want to choose the first one. You are understanding everything, right? Okay. Next, we have a distributed representation. Here we are learning to represent data in a distributed manner with multiple neurons contributing to the representation of a single feature or concept. I have explained this before, so we understand this mechanism, right? Okay, finally, we have our abstraction. I really like this particular mechanism because as we go deeper, you will see how this mechanism comes into play when we have our data set. It learns to abstract away from irrelevant details in the data, focusing on the most important feature or patterns. It's just like the way we operate as humans. There are some things that don't concern you. You are here in this class, AI class, right? What's your business with biology class? Your brain is able to tell you that that's not the class you're supposed to go in. Or you are traveling, and then your flight is for what? You are going to Port Harcourt, for example. What is your business with the one that is going to Enugu? There is abstraction. If we are doing that, our intelligent algorithms can do that. And the mechanism it uses to do that is what we call abstraction. Just imagine the machine doing that.
Oh my God, the same is the urge of knowing what is not planned, like what you think you know. And there's that urge of going for it.
That it depends on how good your activation function is.
We
Is-
have, sorry, ma'am.
All
We
right.
have like 3 roads. You keep taking the first route because it goes straight. You keep using that same route over and over again. But there's this sudden like curiosity that why can't I take the other route? Why can't I just deviate from the first road and cut again? Like
No, I don't agree with you because you are kind of describing a kind of randomization,
yes.
and that the system kind of randomizes and then does it know or it just tries? Is it a trial and error situation?
Yes, it's a trial and error.
Abstraction is not that.
That one is more of a learning, because the system has not created that part to really check it out. That is like, they have seen the features and important to you, and I'll choose to do it.
Because it's using like 3 things. It has learned, it is unlearning, and it's relearning. These 3 things.
I won't say that. I know if I try to get what you're saying, is that the system behaves in a certain way that it's now like jumps from one process into another process and finally gets the right process. No. If you look at this slide, let's go back. There is a deep learning process. And it doesn't just, for example, it just starts from error calculation. Just imagine, it starts from error calculation before it goes to data preparation. And then from data preparation, it now starts iteration. Iterating what? Do you get it? So you have to go through this process first. And that is what the machine does. Humans can do that. Humans can do trial and error. They follow this part, or this part is not working and all that. But remember, you are training a machine here. And then you have to follow the process. Although, by the time it advances, you can give it enough power to become autonomous. That is where the fear is. That you can train a system so well that what you are describing now, it starts to do that. It starts to, on its own, try other parts. And it determines its kind of data. That's where those that have gone ahead, like Elon Musk, and they are wondering where this technology is going. Are we sure we are going to be safe very soon? Kill criminal. And then he just goes and kills someone without trial. But that is what the system is meant to do, in a way. Do you get what I'm saying? We are going, no, but we're trying to introduce some kind of control there. Maybe we'll get there later when there are some kind of ethical regulations in place. Do you get it? So, but for now, you know the processes. This is the process we are trying to describe, and then following it, we are trying to use these different mechanisms of abstraction. I hope, I really, really hope that when we get that advanced, this particular mechanism will kick in maximally. Don't you want that? Don't you want that? Abstraction, like you have your newborn baby and the temperature is very high, and then the AI just drops the robots. You know, it's another arm of AI. Just drops the child inside the freezer.
Describe that robot.
It's not that it's at least people.
Because actually, the body is too hot, and he knows that when you put things in the freezer, it gets cold. So this child needs to be cold. And then to be chill. Okay. So we can develop our abstraction to be more and more intelligent. More and more intelligent, so that it's able, our activation function can run these processes efficiently to give us a very good loss function. Now, in that scenario that I just painted, what's the loss function? It's hitting the roof. The error margin is out of the roof. Do we understand? Okay, so let's go to our last slide. I want to leave here before 12:30. I know you have but so I want to entertain as much questions as possible, okay? All right, so patterns learned in deep learning, the patterns that you learn, just like I told you. Now let's look at our different patterns. Why do we have to learn these patterns? Because in our next class, which is online, I've been informed that, there are holidays coming up. And so 26th is the next class, and that's Boxing Day. It's a holiday, so I'll see you online. Yes, and then the second, which is
it's not like more attractive, more like that it should be extended based on it's not just like from the festive period.
so they will stop the learning.
It's not like stop per se, it's like honoring something.
Yes, I know.
Stopping something.
Stopping something and then continue later. It's not as if we're stopping all together.
Exactly.
I don't know why you said we should continue, but
Because people have plans, families, that's loving.
Boxing Day, so we need to be opening all those gifts.
Don't check why not?
And just 2 hours of
Activation
class. So it's my picture.
activation function.
Our learning rate is so slow then.
The learning rate will be slow.
Error, the loss function.
Yeah. All right. Well, I thought, in fact, I'm meeting you again. We actually had that discussion. I thought I'll be meeting you again after the holidays. I was told you that all of us will just go online, both the virtual learners. I'm sure the virtual learners are happy about that. We'll all
Go online.
go online. I will not be on site. Sorry? This is better, right? For the sake of the online students, on-site students are saying this is better, but we all know that person to person is different in an advantageous manner. I hope I'm not stepping on any toes, but there are situations where it cannot be possible, but learning will still have to take place. I'm sure it's from that perspective that management says, let it continue, because there are situations where it cannot, take place. And truly, one-on-one is always best if we can afford it. So we can see these different patterns. And why, just like I said, why are we seeing the different patterns? We're going somewhere. We want to look at our deep learning architectures. Just like we are talking about structures that are put in place for the deep learning to be able to thrive, for our loss function to be as reduced as possible. What do you use? What kind of architecture do you use to achieve that? And so you have to know the different patterns. We have our linear patterns. Neural networks can learn linear relationship between input features and output labels. And then we have our non-linear patterns, the relationship between these features using activation functions and multiple layers. This time is not a single layer or just what we don't want to use single, because a linear function might not, basically be single, but it's linear. You know what I mean? Be an array or whatever. And then you have the spatial pattern. People should help me with that pronunciation. It can learn these patterns such as images and, videos, and then the temporal patterns such as speech and time series data. So let me ask the question I asked in the first class. For the linear pattern, look at it. We say the activation function tries to help us mitigate this issue. Sorry, snapping. The issue of having only linear results and outputs, right? Now, is the activation function necessary for this pattern? Does it come into play when we are looking at the linear pattern? Do we need the activation function? Yes.
Yes, we
Do we need the activation function? How many of you agree with him that we need the activation function? How many of you feel that we don't need this activation function? When we are discussing linear patterns, the first one then.
We don't.
Think carefully. We don't, right?
Or it can still, if you add it. It still does the function, but it's not like it's needed.
It's not needed. All right. Another. Look at it now. You can discuss. Talk about it. Do we need the activation function? I hope we all remember what the activation function is. You are undecided, or you are trying to reason it. Do we need it? Are you for?
yes, we need it.
You need it. How many of you say yes, we need it? The activation function. Please be bold. Know your stand. How many of you feel that when we are discussing linear patterns, look at the definition of neural network can learn linear relationship between input features and output labels. Straightforward. We don't need the activation function. How many of you say we don't need it? We don't need it. Okay, now, representation of the first group. Why do we need it?
We need it.
Why is it necessary to have it there? If you say yes, it has to be there.
Yeah, because a neural network cannot have. Can I use an example? So, a neural network.
You people should listen to him, or those of you that said yes.
A neural network cannot have. Cannot just stand on its own and just put something in and just remains like that. So you have to have like a processor. Yes, something like that. Yeah. So like something that will put it in place, then gives you an output.
Okay. Do you people agree with him? Has he spoken for you?
Yes.
So all the time, it has to have the activation function.
Yes.
For those that said no, the activation function will not be there. Why did you say it? Counter him.
Because learning,
Who's you or you? Who's speaking?
learning occurs in that way, right?
Sorry?
Learning occurs in that way. Linear relationships are just easier to model. As you all know,
Yeah.
classic model, which is y equals to mx plus c. Right? Basic, right? So the simplicity of that being, of us being able to model it easy is like, just like using a quantum computer to check your emails. Yeah, the small phone can even do that, right? A small basic item. You don't need that much computing power, you can easily learn it. The whole process of going from the input to the output is the learning process. Even if you like acquisition function, that relationship that you're trying to learn is how can this come from this to this? So when you see, okay, it should be gradients in this way to this way.
You can see how linear output.
So are you saying resolving it from this?
Exactly. Just
Okay,
like
sir.
it's too much power for what you can just, you
You don't need all those features to get your
know, you
linear.
don't need that much. You don't need to add so much.
All right.
Sorry.
We need it, and even if it is the minimal, we need it.
Even if it's, the school of thought say it is there, even if what it's going to do is going to be not so powerful, it's just there.
Okay, what I want to say is regarding probably, I'm at the assumption maybe
So this is,
you didn't, the example you gave in the earlier class, you didn't give it to them. So we said something about the linear, the machine learning, where we talked about, to give an example, okay, you know that if you input an information, which is, you say A plus B, you're expecting C. So in that case, the activity or workload is just what linear. But when we talk about activation function, what it helps does is it helps us mitigate weight and biases. Am I correct?
Mhm.
Okay. So which we don't need in linear machine learning. You know, this is an advanced one. In the first class, we talked about machine learning. Then now we graduated to deep learning. So in machine learning now, we don't need activation function to perform our tasks. But now when we move to deep learning, we need an activation function. It's part of it. So he gave an example of using your phone to check your email and using a quantum computer to check your email address. Okay. I don't know how much power a quantum computer has. So, but I want to make an assumption that okay, the quantum computer is the quantum computer. It can do whatever it is it can do. So me checking my email on it, although I don't require much computational power, it's still going to do what it's going to do regardless. It does not remove the powers it has from it. Okay, I'll give an example of okay.
I don't know, our online learners, I hope you can hear.
So
Okay.
I want to give an example of okay, me as a fully grown adult now, I have a certain amount of energy in me that comes with the age or with my physical body. So me needing to carry a bucket that is empty, the energy I need to carry it, or the energy I have to do whatever it is I have to do is still there. And me still carrying one that is that has what I need also. The energy is still there. So the whole story is just that regardless of whether we are regardless, the activation function is part of deep learning and it's just we're going to need it for linear.
Backing up my claim, yeah. At the end of everything, we all want the cookie, right?
The answer is yes.
We all want the cookie, right?
Yeah.
We all want the cookie at the end of everything.
Yeah.
No, please, speak English.
It's money. It's outside.
Yes.
We all want the money back. So, point of learning, well, there's that we're sent to school to get ourselves.
Yeah.
So let's assume we're in a capitalist society. Betterment of
Everybody.
it's starting with business.
Okay.
So what's the point of the business? The business is made to make money.
Yeah.
We let in business intelligence. The point of it is just to streamline the process. So you can make effective process to make your whole operation cost effective, the customers, and then basically get that whole thing right. So if I can get a laptop, or if I can hire employees, or if I can do a process without hiring anybody for cheap, why do you need to hire somebody? Right now let's leave math.
We are actually having a debate.
It's
here.
more. Should I say common sense? Okay. It can move in various ways, right? Now let's go to the world. When computers came,
1 more minute.
things were black and white, things were 2D, basically things were straight line.
Straight line,
You
yeah.
understand? So it's easy
2D.
to run these things before you start getting complexity of breadth or extra layers or something. Application function actually the main aim is to solve complex problems. And non-linear problems are not complex, but then you might need to classify, put them probability forms, stuff like that. If you can do something easier,
All right,
why add this?
Yeah, in this case, they're talking about linear pattern.
Exactly, the linear one is easy. Why make it complex? Like,
But what
I
she
can
said,
go from here, not teleport.
What initially comes to that conclusion that linear pattern is.
Why can't you teleport? I can just find my way to teleport. Why don't you need to now go around? It's not like check and then.
what she's saying is the whole pattern itself. They need activation or they don't.
For linear pattern, no.
You are picking one
Yes,
out
yes,
of,
yes.
out of
Don't.
4
Yes,
or
yes.
5.
You don't need it.
You know, you said.
For checking it.
Okay. Thank you so much. This is beautiful. All right, both of you are correct. Both of you are correct. But one is, one is not correct. What I mean is that you have a point. The group that says we don't need taxation. You have a valid point. If you were to debate it based on your points, you probably will win. But based on what we're talking about and what we are learning, there are so many things that we did not need before when it comes to computation and searching, looking for more and more solutions. We were doing fine. We were doing fine with our voting for. We are doing our thing. We're making our money. We're doing whatever we needed to do. But there is a shift. There's a paradigm shift. There's a new norm. There's a new way. And then this is the new way. Whether you are reporting a linear output or a more complex one, you will not bypass this process. In deep learning, just like our sir said it earlier. It will give you the linear report result if it is supposed to be linear. It will also give you the complex one. So whether it is complex or linear, it will do what it's supposed to do. The fact that it's just linear does not mean it will now come and by force give you the complex one. Do you get it? And then, like you said, this is machine learning, we don't need it. I hope you know that deep learning is actually machine learning, just like I told you, machine learning on stereos. It's actually still machine learning, kind of, but it's an upgrade of the normal machine learning that you cannot divorce one from the other. One is a follow-up of the other. One came because of the other. So one is just like an upgrade of the other. You understand? So please, I just want to correct that you said about, machine learning, does not need the activation function and so forth and so forth. But I hope you get my point. Both are correct. We used to function without the activation function. But right now, we are in the digital technology era. This is deep learning. And this is how the process works. Are we okay? Are we happy?
Yes, ma'am.
All right. I think is all for today. And when we meet the next time, there's something I told the first class. We are going to be talking about deep learning architectures. And you can see the different patterns. Try to map this pattern to different architectures on your own. I probably will I want to try my best to make sure your assignments will be tailored towards research so that you get to learn for your own self most of these things. Bring them to the class. Let's discuss. Okay? Try to map these different patterns to the different architectures and see how they fit. And then get an understanding of how this architecture should be, and then we'll come and discuss the different architectures. I might just put you people in groups, okay? And then, I don't know, we'll work something out for the online learners. We'll put you in groups and then you discuss the different architectures, and they will have an understanding of what these architectures are, representing. Thank you. Are we okay? All right. Enjoy your holidays. All right. Yes, sir. Okay, you travel. Oh, okay. So, but it will be slides. And then maybe by the end of the class, we'll try and watch the presentation and how we are ready to do Okay. Nice to meet you, sir. And some of them.
Thank you. I was able to locate the center last week. I came up to the library to find your office.
We are hidden in the library. The center is hidden inside the library. So if you get to the library, just ask them where's the.
Yeah, that's
Really do ask. Don't ask any student. Some of them don't know. Ask the librarian. Yeah, just ask the librarian, and then the librarian will point you to us.
Who showed the library? But there's an office, and I asked like some ladies over there, and they were like check their office was there. But I didn't really find it.
No. If you just the person there, if you don't see anybody there, anybody elderly, the others are students.
Yeah, the other ladies, like I think one of them carried a baby. Just like that.
No, there are students here that have babies. No, but no problem. What's up? You want to?
I'm not going to sign up on that.
Okay, yes. Yes, that's true. You went online and you were able to.
I have like say I'll just do it when I come to the lab.
Okay, please go ahead.
Yes, sir.
Go ahead. If you are not, no, you can do it online right here. See, meet him. He will guide you on what to do. He wants to be a member of this center, so you are in good hands.
I wanted to ask if there is a resource you can access online on deep learning,
Yes.
like recommend.
On deep learning, there are several.
No, I've not gotten your teaching. Your slide.
That's it. I don't know. I get this one. This is not even my system.
It takes longer times before the.
Okay.
I might not even get it next week.
Send me a message on using the email. I will attach it and send to you. Thank you. Yes.
So I was wondering if we would get the slides.
Yes, I thought that was what I was just discussing with him. So try to discuss with him, and I told him that if you send me, he has my email address. So if he sends me, just send me a message, remind me of the slides. I'll send them to you.
Then I would love to know regarding publications of AI research works. I would love to.
Be part of it.
Yeah.
What's your background?
I did computer robotics education, and